Hello everyone, welcome to the Spintangle. Today it's a continuation of the previous lecture. In this lecture we will be discussing on the number of particles. Let me write it correctly. Number of particles. Before going into that, we will be discussing on the density of states. Okay, density of states, and we will understand about what is called the density of states. Okay, and this is today's lecture is a completely mathematical approach in which we will do some mathematical treatments by representing these things. Okay, the number of particles, say the density of states, whatever it is. Okay, so this thing. So let's move on to the topic that is called. First of all, we will derive the expression of density of states. Okay, first we will understand about this fact. So what is called the density of states? The density of states is the, I am writing this thing, number of microstates per energy level. Okay, this is the number of microstates per energy level, or a certain energy level. Say the number of microstates, say you have d omega number of microstates, okay, in the energy level in between E and E plus D. That means what is the energy interval here? The energy interval here is dE, and you have the number of microstates as d omega. So the density of states will be given as GE is equals to d omega upon dE. Okay, this is the density expression for the density of states. So this is not the actual density of states. Let's calculate. Let's start from the the total number of particles of system. As I am writing this, n equals to integration dn. I can easily write this thing. Okay, what is dn here? Dn is the number of particles in between the energy level E and E plus D. That means in the interval dE. Okay, there are number of particles, say this is dn. Therefore I can easily write that dn equals to what? Dn equals to n. This is a function of E and D. So now from our first equation, what we can write? N equals to integration NE dE. Okay, this is the number of particles here. Okay, now from the expression of distribution function. Okay, what is our distribution function? We have learned about this thing, that what is called the distribution function. I'm writing this thing. Distribution function is written as f of E equals to NE by GE. Therefore what is NE here? NE equals to f of E times G of E. Okay, now the number of particles will become, from this equation, number of particles become n equals to integration f of E GE, and here it is a dE term. Okay, now I am moving to the concept of density of states. Here it is, this is called the distribution function. This is the distribution function, and this is what? This is the density of states. What is density of states? I have written it earlier, that d omega upon dE. Therefore, you can replace this dE by dE upon d omega upon dE. So, to find the total number of particles, what we need to construct. First, we need to construct the what is GE. Okay, GE is equals to d omega upon dE. To find this GE, I will be moving on to this equation. Give this equation as number 1. Okay. Okay. And we'll be back to this equation later. Okay. Therefore, GE equals to d omega upon dE, where omega is what? Omega is number of microstate, number of ways, okay, in which the internal arrangements, okay, the number of internal arrangements, okay. Omega in case of classical ideal gas, what is this? This is GS times 1 upon HF DFQ DFP. Okay, we know this thing from our earlier concepts. Omega is equals to this. Therefore, writing this omega as omega equals to GS times 1 upon H cube integration D cube P D cube P, because we are taking classical ideal gas in 3 dimensions. Okay, therefore F will be what? F will be 3 for monoatomic gases. Okay, for monoatomic gases. Okay, there are no constraints in this system. That F is equals to F is the degree of freedom. Here GS is what? GS is called spin degeneracy. Spin degeneracy. Okay, this is given as 2s plus 1. Number of degenerate states are 2s plus 1, or where s is what? S is the spin of the particles. Okay, so now integrating this thing, as there are 2 arguments on this integration, therefore I am giving 2 integrations. The first integration will be on the Q and the second integration will be act on the P. Therefore, what will become? The GS equals to integration, I am writing this thing, integration d cube Q integration d cube P upon H cube. That means it becomes GS. It becomes GS times, what is this? This is the volume, spatial volume. This is okay, and this is what? This is the volume in the momentum space, and we know the volume element of the momentum space is dqp. Therefore, the volume in momentum space will be written as GS into V by H cube integration 4 pi p square dp. Okay, now what is p square? Here I am writing this p square. We know p square equals to what? 2me is from the kinetic energy expression. Differentiated this thing 2p dp and here 2m de. Therefore, what does it become? dp becomes, I am closing this thing with this thing, p dp becomes mde upon p. From this thing p will be what? From the above equation p will be root over 2me. Therefore, it becomes mde upon root over 2me. Okay, now the dp is replaced by this thing to make the total expression as a function of energy. Okay, I am putting this thing. Okay, GS equals to what? V upon H cube. 4 pi remains the same here. P square equals to what? 2me, and dp becomes what? mde upon root over 2me. Okay, this is the expression of number of microstates. Okay, so writing this thing carefully. Just okay. Now solve this equation. How to solve this equation? Everything is constant except this e. Therefore, what is become? Here is a e and here is a e to the power half. It becomes e to the power half here inside this, and all the term will be opted out from the integration. GS times V upon H cube. Here is a 4 pi. Here is a I think there is a root over 2m term. Here is a 2m term. There is root over 2m. Okay, there will root over 2m times m integration e to the power half dE. Check this thing. Check this thing. I have opted the constants out from the integration. Okay. Yeah. Now therefore what does it become? Therefore it is gs times 4 pi v upon h cube, 4 pi v upon h cube. Here it is sorry, here it is root over 2m times m, and here will be a e to the power 3 by 2 term, I think so. It is e to the power 3 by 2 upon 3 by 2. Okay, so in solving this integration, okay. Now this is what, this is omega. Okay, now this is your omega, this is your omega. Okay, so density of state will be what? Density of states will be what? Oh, just wait, it's not the suitable color to write. Density of states will what? GE. GE will be given by as d omega upon dE. Okay, therefore differentiate this thing, differentiate this omega, this the number of microstates, by E. This becomes, check this thing in your copy, that differentiate only this differentiation will be act on this e to the power 3 by 2 term. Okay, on this e to the power 3 by 2 term, and this differentiating this thing, what does it become? It becomes 4 pi v upon h cube root over 2m times m e to the power half. Okay, this is what? This is the density of states. Okay, therefore density of states will determine GE equals to 4 pi v upon h cube root over 2m into m e to the power half. This is the expression for the density of states. Okay, box this thing. This is the important expression for the density of states in case of classical ideal gas. Okay, now I am moving to the next. What we was doing, our main topic was focused on the number of particles and energy. Okay, so fine, to find number of particles from equation 1, n was what? N was given by integration f of e g of e into ge. Okay, in case of Bose-Einstein statistics, what? The f e 1 upon e to the power alpha plus beta e minus 1. Okay, in the previous class we have discussed on this topic. And what is our ge? Ge is 4 pi v upon h cube root over 2m times m e to the power half, and here it is a dE term. Okay, now opt out every constant terms from the integration. It becomes 4 pi v upon h cube root over 2m into m, and inside the integration we have e to the power half dE. I am writing this e, sometimes I am writing this e as epsilon, and sometimes writing e. E and epsilon are same. Okay, e and epsilon are same in this calculation. I mistakenly done this thing. Okay, sometimes I do it. Okay, because I used to write e as epsilon. Okay, I used to write in case of signing my name also. Okay, my name or writing any other's name. I prefer this epsilon. Okay, beta e minus 1. Now you have to solve this thing. To solve this integration, you have to solve this integration. Here the integration is on this factor. Okay, this is the argument of the integration, that is the function, whatever is called the dependency of the integration. And therefore the number of particles. Say you have a classical ideal gas, okay, in which the gas molecules are arranged like this thing. Okay, and the energy of these particles can be from 0 to infinity, okay, because energy maximum energy could be here infinity, and the minimum energy can be 0. Therefore it becomes the limit of the integration becomes 0 to infinity. Now solve this equation. Okay, how to solve this equation? Let the standard type of solution beta e equals to x. Okay, beta is what? 1 upon kt. Therefore e by kt equals to x. Therefore e will be what? ktx. Now de will be what? kt times dx. This is the e, this is the de. Okay, now this is the number of particles. Now from the number of particles expression, giving this equation 2. Okay, from equation 2, what we can write? Say n equals to 4 pi v upon h cube 2m times m. There will be a 0 to infinity term, and here it is a ktx power half, because e is ktx power half, e to the power alpha plus x minus 1. Here it is a kt into dx. I think I am correct. Okay, I think I am correct. Check this thing, because this is the d, this is the d. Okay, oh, just wait for a while. Now let me check this thing out. 4 pi v upon h cube, here it is a 2m times m, and here kt to the power 3 by 2 will be opted out from the integration, and the integration will be on x power half dx e to the power alpha plus x minus 1. I think I'm done. Okay, now just wait for a while, just wait for a second. Have I mistakenly done anything? Just let me check this thing. Okay, let's take another term. Okay, 4 pi v upon h cube root over 2m times 2m kt to the power 3 by 2. Up to this thing is okay. Let's introduce one thing, that's root over pi by 2 and 2 by root pi. This term will go with this term and will cut with end with nothing. Okay, therefore x power half dx e to the power alpha plus x minus 1. Why I have written this thing? To make this 4 pi term as 2 pi. Okay, make this 4 pi term as 2 pi. This now this becomes, you can check this thing from your calculation. I'm writing this thing v upon h cube. Here it becomes, cut this thing with this, it is 2 goes with 4, this becomes 2, and this and okay, now this okay, here will be a 2 pi m k t. This root pi goes with this pi, becomes root 3 by 2. Okay, power 3 by 2, and here is a power 3 by 2 root 2 okay, 2 pi m k t to the power, and here it is a extra root over 2 pi. Okay, and here it is a 0 to infinity. Check this thing by your own. Okay, 0 to infinity. Okay, 0 to infinity, and here it is x power half, and here it is e to the power alpha plus x minus 1. Here it is a dx. Okay, now we know one thing. Just wait, we can write this thing as, say I am taking this integration. Okay, just wait. As a function of x. Okay, this is x as a function of x. This becomes v upon h cube 2 pi mkt. This is 3 by 2 power 3 by 2. Here it is with this thing, with this thing also, I am taking this thing as, say, f of alpha. This is a function of alpha. I am writing f of alpha, f1 of alpha. Okay, f1, writing this thing just. Okay, this is what, this is the number of particles. Okay, now just wait, where f1 of alpha is what, is root 2 by root pi, 2 by root pi, and here it is a 0 to infinity term, x power half, and there is a dx, and e to the power alpha plus x minus 1. Okay, we know a is our what, a is our 1 upon e to the power alpha. Okay, 1 upon e to the power alpha, that is e to the power minus alpha is a from our previous lecture. Okay, if a is less than 1, therefore f1 of alpha becomes summation. Just remember this thing, not right, I am calculating this thing because your purpose, just remember this thing. Okay, it becomes a to the power r, and here is a r to the power 3 by 2. Writing this thing, just, you do not have to remember this thing. Okay, if a is less than 1, for f1 of alpha, f1 of alpha becomes alpha max here, its value is 2.612 for a equals to 1, and f1 of alpha minimum becomes equals to 1, a for a very less than 1. Okay, if a in our case a is very less than 1, so from our number of particle expression, what we can write, n equals to v upon h cube, here it is a 2 pi mkt to the power 3 by 2 term, and here will be a. Okay, this is the total number of particles. This is the total number of particles. You have to remember this thing. Okay, sometimes the total number of particles in case of classical ideal gas may be written as only this thing without, except this a, but this a will be very useful for our next lectures, which is based on the I think it is Bose-Einstein condensation. Okay, so this is the number of particles. Now I am moving to the total energy expression. Okay, right, this thing, total energy. Total energy in our case, what will be this? Just try to remember this thing. What is our total energy? How to write this total energy? Okay, just okay. Say the total energy is written as capital E. Okay, and it is written as E times dn. Okay, this is the number of particles. Say integration dn is the number of particles, and each particle having energy E, epsilon. Okay, this is all. Now integration epsilon, what is dn? In our case, dn is fe times ge times de. Okay, now omega E is what? Gs times v upon h cube, here 4 pi p squared dp, and from this we replace this thing as I have did this thing, 4 pi v h cube and just wait, I'm doing this thing, I'm doing this. So we have p square equals to what? 2me, and 2p dp is what? 2m into de. Therefore p dp will be what? mde upon m. dp will be what? mdp de upon p, and here it is becomes mde upon root over 2me. This is our dp. Okay, put this thing on the equation. So in our equation it becomes omega e becomes, just wait, 4 pi v upon h cube. Here it is a 2me. Okay, and here it is a m by root over 2me, and here it is a de. Okay, now 4 pi vm upon h cube. These are just mathematical treatments. Okay, vm upon h cube, and here will be a 2m e to the power half term, and here it is a de term. Okay, now density of states will be what? Now density of states means number of microstates per energy interval. Okay, that becomes ge equals to d omega upon de, and it is the first derivative of with respect to e. Therefore you can omit this integration, okay, and write the all other remaining terms. Okay, that becomes 4 pi v upon h cube root over 2m. Here it is a m and e to the power half. Up to this thing we have did it in case of our number of particle expression. Okay, now that I am moving on to the total energy expression. Okay, what is our total energy expression? Our total energy expression is given as E equals to integration 0 to infinity. Say it is a epsilon. I have written this epsilon 1 upon e to the power alpha plus beta epsilon minus 1. Here it is a 4 pi v upon h cube root over 2m times m e to the power half, and here it is a d epsilon. These are okay. This is a huge mistake which I used to do in case of calculating this thing. Now opt out this 4 pi v upon h cube root over 2m because these are constants, and here it is a extra pi root over pi by 2 and 2 by root pi term. Okay, this is the extra term to make the simplicity. Okay, 0 to infinity. Here it is becomes e to the power 3 by 2, not half. E to the power 3 by 2 upon exponential power alpha plus beta e minus 1. Here it is a de. Okay, now again solving in this on the same process. Okay, which take beta e equals to x. Write this thing on your copy. Okay, write this thing on your copy. I am not doing this thing. You have to solve this integration, and the value of the integration becomes, I am writing this e equals to 3 by 2 kt, and here it is a v by h cube 2 pi m kt. This is the homework. This is your homework to do this integration. Okay, 2 pi m kt to the power 3 by 2, and here it is the integration term. There will be another integration term which I am writing this f2 alpha. Okay, this is the expression for the energy. Put a box on this expression for energy. Okay, this is the required expression for the energy. Now up to this thing it is okay. Okay, this is the energy expression. Now I am moving to the E by N expression, that the energy upon number of particles. What does it become? This becomes 3. From the number of particles expression you can check this thing. Put the value of number of particles, put the value of energy. Okay, and you will be getting 3 by 2 kt here it is a f2 alpha by f1 alpha. Okay, for e to the power minus alpha very less than 1, this is what, this is a, this is our a, very less than 1, e by f2 alpha becomes equal to f1 alpha. Okay, and they will be both equal to a. Okay, therefore these two terms will be cancelled out with each other, and e by n becomes 3 by 2 kT, and the total energy in case of classical ideal gas will become E equal to 3 by 2 nkt. Okay, this is the well-known equation, well-known expression for classical ideal gas energy. Okay, gaseous energy. Okay, up to this thing, this is okay to you, I think so. And this lecture will be terminated on this thing only. Okay, and on the next lecture we will be discussing on the Bose-Einstein condensation process, and the process will be very interesting. Before going on to this topic, you have to remember each and every term of this topic. Okay, so therefore this will make your path of understanding the Bose-Einstein condensation simpler. Okay, so thank you for being with us. Like the video, subscribe the channel.